Okay, so instead of traveling literally in circles, we are doing some sort of periodic movement. So maybe we're going backwards and forwards. Child on a swing is the classic. So it starts, the child accelerates, forwards, and he goes through the middle, where he's at his equilibrium position. And then at the end, he's accelerating backwards. He might still be going forwards as he approaches the very front of his swing, but he started to accelerate backwards. He started to slow down. The maximum speed is when he's in the middle. That's the real whoosh of the swing. So when we talk about simple harmonic motion, you don't necessarily need to interrogate each word within SHM, but you need only understand that it's oscillating motion of an object with a specific mathematical format. Have I frozen? Yeah, there we go. Sorry, my PowerPoint was playing up for a little bit there, which has the following two features. The magnitude of the acceleration is proportional to the negative displacement. And so the two features are that it's proportional to the displacement and it's always pointing in the opposite direction as the displacement. So anytime you have a system where the acceleration is proportional to the negative displacement, you can guarantee that you're going to have simple harmonic motion. And this happens perhaps more often than you would think. Okay, if we said acceleration, look, there's direct proportionality between a and minus x. We are at liberty then to say that a is equal to negative kx, where we can make up our own constant of proportionality. Now, for reasons that will be mathematically convenient later, so this is a choice that is based purely on mathematical convenience for now, but our constant of proportionality, we are going to choose to be this thing called omega squared. And that is because that will turn out to be, omega will turn out to be our good old friend, angular frequency. Now you might at this stage say, James, look, I thought omega was angular speed. And you're right. In the context of circles, it is angular speed. In simple harmonic motion, we instead call it angular frequency. And that's because when you talk about a circle, you really are talking about sort of how fast around the circle you're going. It's a bit more complicated in simple harmonic motion. This is one of the reasons I say they're not the same thing, even though they have mathematical analogues and they're related. The boy on the swing is not always turning through a physical angle at the same rate. You know, there's a moment where he stops, there's a moment where he goes at his maximum speed, and so on and so forth. So instead of physically splitting a circle up into 2 pi radians, we're going to conceptually split up a motion, a repeated motion, into 2 pi segments, and say how far through a repeated motion is he? If he's halfway, well, then he's pi radians through that motion. And then if he's all the way through that motion, he's at 2 pi radians, ready to start again. So similar but related concepts. Okay, all the maths from before still applies, don't worry. So omega is still equal to 2 pi, and that's still equal to 2 pi over t. Great, so don't chuck away your maths. The maths is still useful. The maximum displacement from the equilibrium position, we are also going to define as A. So for example, if I have a mass on a spring, and I pull it down and then I release it, It's got an equilibrium position here. And perhaps its maximum position is up here. Ding, 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 ding. It sort of springs back and forwards. The amplitude, and it's important to make this distinction. The amplitude is not the full range from the peak to the trough. It is the maximum displacement from the equilibrium position. Okay, so it's only this distance. It is not from here all the way up to here. A is independent of the time period t of the oscillation. So whether my spring or my child or whatever this system is, whether it's doing massive oscillations or very little ones, its time period is the same. So if it takes 1 second to do a little one, even the massive one, it will still take 1 second. Okay. Right. So the amplitude is the maximum value that x, our displacement, will take. If x is our displacement at a given time, a is the maximum value of that displacement. Okay, so at some point, we will get the situation where the maximum acceleration we can get, if we look at this equation back up here, the maximum acceleration we can get is minus omega squared of the maximum displacement, which we've defined as a, our amplitude. Okay, I promise, we'll bring all these concepts together further in just a moment. An example of a simple harmonic oscillator is a mass m on a spring with spring constant k. Okay, yep, this makes sense. The force here is equal to minus kx. Therefore, the acceleration is minus k over mx. Therefore, you can see the acceleration is proportional to negative x. Therefore, we're going to get our simple harmonic motion. Here is its equilibrium point. Here is it when it's at its maximum displacement. Here is it when it's at some intermediate form of displacement. Okay. Again, some of these the formula for these two systems are given on your data sheet. For the purposes of today, we're going to have to move a little faster, but you do not need to necessarily worry about deriving these. You're given them in your formula sheet, but you're given that the frequency, bear in mind not the angular frequency, just the frequency f, is equal to those two systems. Okay. You can then use all the maths we've covered so far, multiply the frequency by 2 pi, and you'll get the angular frequency, and so on and so forth. Okay, exam question. Describe and explain how the period and maximum acceleration of the oscillation of a pendulum depends on its initial displacement. Okay, 2 marks, 1 mark for describe, 1 mark for explain. The period, so if you're given this for a pendulum, the period is going to be 1 over f. So the period will be 2 pi L over G. So it depends on what planet you're on, because it depends on the gravitational constant or the gravitational acceleration. And it depends on the length of the string, but actually it doesn't really depend on anything else. Initial displacement determines amplitude A, and period is independent of this. Maximum acceleration is given by A max is minus omega squared A. Since omega is independent from A max is proportional to the initial displacement. Okay. So the period does not depend on the initial displacement, but the maximum acceleration does, because acceleration for all simple harmonic motion systems is proportional to displacement. So the maximum acceleration is going to be proportional to the maximum acceleration, maximum displacement.